Today I'm going to talk to you about another gas law, Gay-Lussac's law. You use this one when your volume is not changing. So this one is going to be the relationship between pressure and temperature. The form that we use it, our starting conditions, our first pressure divided by our first temperature is equal to a constant, and our final pressure divided by our final temperature is equal to the same constant, so we can set these two equal to each other. You will be given 3 of the 4 variables, and you will have to solve for the 4th. If we think about pressure and temperature, if you think about a tin can of SpaghettiOs, if we put it into a campfire, the size of the can can't change much, but as it heats up, inside the pressure will build up because the molecules will move faster at higher temperatures. They'll be hitting the sides of the container harder since they're traveling faster, and the pressure will go up. So as temperature goes up, pressure goes up. As temperature goes down, pressure goes down. So they go the same direction. Either they both go up together or they both go down together. And this is called a direct relationship. Here's our first problem that we're going to work out. If a propane tank attached to a grill sits in the sun, the temperature rises from 24 degrees Celsius to 65 degrees Celsius. If the pressure in the tank at 24 degrees is 2.5 atmospheres, what is the pressure at 65 degrees Celsius? So we're going to pull our variables out of our problem. The temperature rises from 24 to 65. So temperature 1 is 24, temperature 2 is 65. And then we're told that the pressure was 2.5 atmospheres at 24. So 2.5 and 24 go together as our starting conditions. And it asks, what is the pressure at 65? So at 65, our pressure is what we're trying to find. That's going to be our X. Now remember, whenever there's temperature in a gas law, you have to change it to Kelvin. So we have to add 273 to both of our temperatures to get them into kelvins. So 273, 297 is 338 Kelvin. So we're not going to use our Celsius anymore. We're only going to use the Kelvin. Remember, our equation is P1 over T1 equals P2 over T2. So we're going to fill in our variables. Pressure 1 is 2.5 atmospheres. Temperature 1 is 297 Kelvin. Pressure 2 is what we're trying to find, and since our pressure 1 is in atmospheres, our pressure 2 is going to come out in atmospheres, and our final temperature is 338 Kelvin. The easiest way to solve this is to go ahead and cross multiply. So I'm going to take 2.5 times 338 equals 297 times X. 338 times 2.5 is 845. I'm going to divide both sides. Since this is times X, I need to divide by this number to get it off of this side. But if I do it to the right side, I've got to do it to the left side to keep them equal. So this cancels, and I have 2.845 atmospheres equals X. I go back to my original problem, and I've got 2.5 atmospheres as my starting, so I'm going to just keep 2.8, 2 significant digits, and that's our final answer. We will work one more. If you want to look at the problem and pause the video, you can work it out and then hit play to check your answer. Here's our second problem we're going to work out, and it's going to have some conversions that we need to do. From our problem, our starting pressure is 1.3 atmospheres, ATM. It's at 20 degrees Celsius. It's asking what temperature, so this is going to be our X. Will the pressure be 295 kPa? So as we know, for temperature, we need to add 273, get 293 Kelvin. So that's that's what we're going to use for T1. T2 is going to come out in Kelvin, and if you're asked for Celsius, then you would need to subtract 273 to get it to be Celsius. This problem doesn't designate, so you can probably leave it in Kelvin with no issue. But we do have another problem. This is atmospheres, and this is kPa, pressure. And I've given you the pressure conversion factors up at the top. We need to either get both of them into atmospheres or both of them into kPa. So I'm going to go ahead and change my atmospheres into kPa. It doesn't matter which way you go, the problem will work either way. So to change my atmospheres into kPa so that it will match, I need a conversion factor. I go up here to get my numbers. Now since I have atmospheres there, I need to put 1 atmosphere on the bottom, and 1 atmosphere is the same as 101.3 kilopascals. Our atmosphere unit cancels, and we're left with 1.3 times 101.3, which is 131.7 kPa. So now we're going to plug these numbers that we have into our equation, and remember to use kilopascals, Kelvin, and this will come out in Kelvin. So we want to use the ones that we calculated, not the starting ones. So we put these numbers in. So P1 over T1, 131.7 over 293 equals P2 over T2, 295 kPa over X. Then we're going to cross multiply to find our answer. We're going to have 131.7 times X for that diagonal, and on the equals 293 times 295 for that diagonal. So we do this times this equals this times that. On our right side, that gives us 86,435. On the left, we have 131.7x. We want to get rid of the 131.7, so we divide both sides by that. It will cancel on the left and just leave us x. On the right, we need to divide those numbers, and we get x equals 656 Kelvin. If you're asked for Celsius, just subtract 273. So this is Kelvin. We subtract 273 to get Celsius. Notice our pressure went from 131 to 295. Pressure went up, so temperature should go up, and it went from 293 to 656, so it definitely went up. I hope this helped. Please come back to view other videos on other topics in chemistry. Please like and subscribe. Have a great day.